everyone. Today we are going to be talking about isotopes and learning how to calculate the average atomic mass for different elements found on the periodic table. So, just as a review, I first want to go over what isotopes are. And remember, they're atoms of the same element, but they have different masses because they have a different number of neutrons. So, if we have atoms of the same element, they're going to have always the same number of protons, but we can have different numbers of neutrons. So the average atomic mass is found on the periodic table right here at the bottom of each square, and it is the weighted average mass of all the isotopic masses of that element. Now, the unit for that is the atomic mass unit, which is abbreviated AMU. We use a mass spectrometer, or we don't, but researchers use a mass spectrometer that which separates particles by mass and then measurements of each of those. And then we use that data in class to go ahead and calculate the average atomic mass. The relative abundance is the percentage of that isotope that occurs in nature. So all of the relative abundances, we're going to see them as percentages in our problems, and it should always add up to 100%. Now, that might be like a 70-30 type of thing, or we could have multiple that would be 60, 20, 20% each. And just remember that our isotope notation looks something like this. And the next example we're going to do is calculate the average atomic mass for nitrogen, which has two different common isotopes, nitrogen-14 and nitrogen-15, both having 7 protons, but different numbers of neutrons.
So you saw on that last board that the average atomic mass is going to be closest to whichever isotope is most abundantly occurring in nature, right? So we're going to see these different abundances. In this example, it says nitrogen consists of the isotopes N14 with the isotope mass of 14.003 AMU. And that occurs 99.636% of the time in nature. And nitrogen-15 with an isotope mass of 15.000 AMU, which occurs 0.364% of the time in nature. What is the average atomic mass of the two isotopes? Now, if we're just looking at these, we see that N14 occurs way more often than N15. So when we actually find the average atomic mass, it should be much closer to this 14.003 versus closest to 15. It should not be as close to 15. Right? So now here's our formula for calculating the average atomic mass. We're going to take our relative abundance, right, which I've written here as percent abundance, divided by 100, right? And all that's doing is putting that into a decimal form for us. We're then going to multiply for each isotope. We're going to multiply that by the mass in AMU of that isotope. We're going to do that same thing for the next isotope that occurs, right? So we're going to add this together, add this to the next percent abundance, divided by 100, putting it in decimal form, multiplied by the mass in AMU. If there are more than 2 naturally occurring isotopes of that atom, then we are going to, or of that element, then we are going to continue to do this. Plus the percent abundance divided by 100 times mass, plus the percent abundance divided by 100 times mass. All right, so however many isotopes there are, that's how many times we're going to need to do that step. So in my example from up above, the purple is all of our nitrogen-14. So it occurs 99.636% of the time in nature. We're going to divide that by 100, and we're going to multiply it by the mass in AMU. The mass of nitrogen-14, 14.003. 14.003 AMU. Right? Then we're going to add the next isotope. It occurs 0.364% of the time. Divide that by 100 and multiply it by the mass. For N15, that's 15.000 AMU. Now, I've included this intermediate step. You don't necessarily need to use this intermediate step, but if you want to do each piece separately, then that's what I've done here. All right? So when you do this math right here, you get 13.952029 AMU. When you do this math here, you're going to get 0.0546 AMU. Now you may be wondering why I'm not rounding for sig figs right now. we only want to round for sig figs at the very end, right? So with any calculations, we're only going to round for sig figs at the very end.
Well,
so when we add these together, without rounding them, well, keeping them as unrounded as possible, we get 14.007 AMU. This has been rounded for sig figs, right? So again, round for sig figs at the very end. Dogs are having a great time.
Okay, so here's an example that you guys are going to try in a minute, and then you're going to pause it, and you'll try it on your own, and then we'll complete it for you on the board, and you can check your answer. So just a reminder of when you're plugging all of this into your calculator, to use your parentheses, right? We want to make sure that we use these parentheses and then add in between, because we want to type this all into our calculator at once instead of trying to round in between, because we might end up with the wrong final calculation. So this example is a little bit different than the last one for one reason. And as you can see, we're not given the mass for each of the different types of isotopes. So sometimes that's going to happen in class or on a test, and all you do is you have to use the if no masses are given, you're going to use the mass number, or A, remember from our isotope notation and isotope tables. You're going to use A because that is really close to the mass, because remember, 1 proton and 1 neutron are about equal to 1 AMU. So we wrote down the formula here for you guys already, because every single time, no matter what kind of problem you're doing, you always have to write your formula down first. I know we're sticklers, but I promise that it's for your own good. And so we wrote it down for you here already, and this only has 2 different types of isotopes, so we only need 2 parts to our equation, or to our formula. So chlorine has 2 naturally occurring isotopes. Chlorine-35, which has an abundance of 74.8%. Okay, that means that 74.8% of the chlorine that's found on the surface of the Earth is chlorine-35, whereas 25.2% of the chlorine found on Earth is chlorine-37. So if you calculate all this, plug everything in, you're going to go ahead and figure out the average atomic mass, which should be closer to 35 than to 37, because there's more chlorine-35 occurring naturally than chlorine-37. So you guys can go ahead and pause the video right here, complete your plug everything in, complete your calculations, round to the proper number of sig figs, don't forget your units, and then we'll go ahead and then you can press play, and we'll go ahead and continue to tell you what's going to happen. Okay.
Yep.
So what do you want to say? Okay, so chlorine-35 has an abundance of 74.8%. So 74.8% divided by 100 times 35 AMU. Okay, that 35, don't forget that AMU in there. This is where we're going to get our points marked off, right? And then we have 25.2% divided by 100, which is equal to, or times 37 AMU, equals, you're going to plug that all into your calculator at the same time, so practice that. And our final answer is 35.504 AMU. Now, sorry, sig figs always, sig figs. I know. So, how many sig figs are we going to round to? 2 here, 2 here, so we need our total of 2 sig figs. So that is going to round to 36 AMU. You can see that we were right in between 35 and 37. So sometimes when we end up with just using our mass number to calculate our relative abundance, we're not quite as accurate, so we might not be quite as close to our more natural or our more abundant isotope.
Let's look one more time. I didn't point this out, but I want to. So if we see our final in our last one, our final average atomic mass that we got was 14.007. Remember, the abundance of nitrogen-14 was way higher, so we were closer to the 14.003 with our 14.007 AMU.
Okay,
So,
thanks for watching.